Hello and welcome to Differential Equations, Chapter 1, pointers, shenanigans, stuff, whatever you want to call it. I'm just going to give you a few pointers for not just Chapter 1, but also for the future. Talk a little bit about differential equations, put some things in context for everyone. So let's start first with the notion that differential equation is an equation which contains derivatives and functions and values, independent variable, and so on. And its solution is a function. So we can just start that differential equation is equation containing unknown function and its derivatives and possibly an independent variable and possibly other functions. So we can denote that as f of, and now I can say t, y prime, y double prime, three dots right there, equals to maybe some function f of t or g of t. So capital F and lowercase f are not the same. Capital F is where you take the entire differential equations, put it all together, and then this f at the other end, this one over here, this f could be what we call a driving term. You hopefully learned homogeneous versus non-homogeneous equation, when this is 0 and it's not 0 and so on. We'll have much more of that in chapters 2 and 3. So that's the differential equation, and now solution is a function y of t, and that's where solution is explicit, or relation some kind of f of t equals to c implicit. Now, for those of you who did not take Calculus 3, you might not understand what I just wrote over here. So let's just quickly say, so if I have a solution to be y equals 3e to the 4x plus 6, so this would be called explicit, because we are able to separate y, which is the name of the function, and then x or t or whatever independent value with all of the things that are happening to those x or t on the other side. So that's explicit. Now, implicit would be the one where you cannot separate them. You might be remembering implicit differentiation, right? For instance, equation of the circle is not a function, and you cannot write it as y equals everything else. If you can write it y equals everything else, then that's explicit, right? But for instance, circle, let's say x squared plus y squared equals to 9, is implicit. It could be a solution to differential equation. It's not a function, right? It could be solution to differential equation. It's not a function. So that could be a possible solution. So your solution is a function, or your solution is a relation, something like a circle, or it doesn't have to be a circle. I mean, it could be literally anything else, but you cannot separate y from your x's and t's. Now, our differential equation in the beginning, right, usually in chapter 1, pretty much all of your problems are your independent variable is x, like you're used to, f of x, right? But as soon as we start using applied problems and so on, we quickly switch for independent variable to be t because it represents the time. Right? Calculus is study of motion, study of change, and things change in time. Things change with time. So generally, we like to measure everything in respect to time. Therefore, it's going to be f of t, x of t, y of t. We're going to have a lot of these functions, and generally, they will all be of t eventually, right? Starting in chapter 2 and then 3, and later on, you will see this x phased out as independent variable. So the sooner you get used to having a t as your independent variable, the better. So that's another cool pointer. Now, when you solve your differential equation, because differential equations contain derivatives, generally you will be integrating or doing something like that. It spits out that plus c, which could be also, through algebra converted into times c or whatever. Now, that c can be computed if you have initial point. If you do not have initial condition, initial point, initial value, if you don't have that, there's all different names for the same thing, then you can't compute c. So you will leave it as c. But when you have a value given, then you can compute it. So one of the examples of separation of variables, which is one of the basic methods to solve, I believe that was in 1.3, right? You might run into a problem that it's a separable problem, and then it might have this point given to you. So you will just now, obviously what I do here for separation of variables, you will continue doing this for the entire course for every a new method you learn. So separation of variables would go something like this. You have, let's say, xy squared y prime is equal to, let's say, 3x. Right? Let's say this is your, right. Now, one thing that we need to learn very quickly in this class is that the y prime is a terrible notation, okay? We do not use y prime because you can't do separation of variables, and it's very easy to kind of miss the derivative because it's just this tiny little line up there, especially right using the pencil and so on. So we write the good notation, which is the Leibniz notation, dy over dx. Now, that's the pro notation. You want to be a pro? You start using that. Let's say you want to make, you want to get a tattoo, and you tattoo this. It's a joke, right? This is the stuff to tattoo. Look at that. It's going to cover like a lot of square inches right there. Anyway, so now when you go and you solve this, you write it properly first, which is dy dx equals to, this is going to be, I shouldn't have done this. How about 3x plus 2? Huh? Whatever. There we go. So now, what we are going to do is we are going to separate the variables. We are going to put all of the variables of one kind, which are x's, on one side of the equation, and all the variables of the other kind, which are in this case y's, on the other side of the equation. And for us, that is clearly dx needs to go on this side, which means that this x also has to go to the other side. So y is already in the numerator and it will stay on the left. Therefore, this one stays on the left because we want to have all of the same variables on one side. So we're going to say xy squared dy is equal to 3x plus 2 in parentheses dx, right? So I move that dx to the other side, and now divide both sides by x. Now we know that x can't be 0, right? And we're going to have 3x plus 2 over x dx. There we go. So the variables are now separated. You cannot do this for every equation. Only the equations that are separable equations can be solved by using separation of variables. Right? Just like you can't take product rule for every derivative you see. It is only reserved for derivatives that are a product. So this book is going to teach you 10, 15 different methods, and you use those methods when it's appropriate, right? So you have a whole bunch of derivative rules, a whole bunch of integration rules. Now you're going to have the whole bunch of different methods to solve equations, and you use the appropriate one, right? Whatever the situation is. So now we are separated all of this, and this is the time when I'm going to hit both sides with the integral sign to solve, right, the equation. Now on the right hand side we are getting y cubed over 3, and you can put, let's put plus c. So you could put plus c on the left, but then you will have another plus c on the right, and then you say, well, those might not be the same. Then I'm going to call one c1, then I'm going to call c2, and then you're going to subtract. It's just mess. Don't do all of that stuff. Just put plus c on one side, because eventually, if you are to write plus c1 on this side, plus c2 on this side, and then you subtract c1, you get c2 minus c1, and then you call that a c. It's just a lot of mess to kind of go through all of those steps for no reason. Just when you integrate the right hand side, you just put plus c on one side, and that's good enough. So to integrate this, we are going to divide this, get 3 plus 2 over x, and we're going to integrate now, because now it's easy, right? So we have 1/3 y cubed is equal to 3x plus 2 ln absolute x, and here is that plus c. Now, if you want to be a pro, right, you are going to attempt and solve for y. So you will multiply everything by 3 first, right? You will get 9x plus 6 ln absolute x plus, and here is the thing that annoys a lot of people. Yeah, you kind of want to write 3c, but you don't have to. C's will absorb multiplication or division by a constant, so there is no need to write 3c. I know it's going to trigger a lot of you, but really you will get used to it in this course. You do not have to multiply c by 3. So you need to multiply these two, right? And then the third one times 3 will just get absorbed by c, and it's still a c. And now we're going to take a cube root of both sides. Now this one has to stay under the cube root. So when I cube root both sides, it will be y equals cube root of, and I'm going to have 9x plus 6 ln absolute x plus c, all of this under a cube root. Now, the solution is explicit because I was able to write y equals everything else. So it's explicit solution. Also, these solutions are known as general solution. And the reason why it's known as general solution is because this plus c over here, right, would shift the function depending on what the value c is. Now, if you want to compute particular solution, we need initial point or initial value. There are a whole bunch of ways in which they are going to give you the point, right, that you can use to compute c. Now, since we have ln of x, right, of absolute x, we are allowed to use any value for x except 0. ln of 0 is negative infinity, so that would break our equation in this case. Now we can also see that we can't use 0 in this row here because you have divided by x, right? You also said between these two, right, you divided by both sides by x. You are not allowed to divide by 0, so that would eliminate the value of 0. But, you know, if you have, say, let y of, I don't know, y of 1 be equal to 19. It doesn't really matter, right? You are going to have some kind of a point. This over here is point and that's 1,19, right? X and a Y. So now, when you have a point like this, right, which is called initial condition, let's say, or you can also call it initial value. Right? If you have something like that, we can calculate C. Let me write that in blood. Now we can calculate C. So if we are calculating C, we can go and so now we just plug in all of the values. We plug in all of the values in the problem, and we can. So let's go with 19 equals cube root of. Now that's going to be 9 times 1 plus 6 times ln of 1 plus C. And as you can see, value C is the only value of C is the only unknown value in this expression, and you can calculate the value of C. So ln of 1 is 0, right? So this mess now is 19 equals cube root of 9 plus C. And we cube both sides. So it's 19 cubed. Okay, fine. You take the abacus and you figure out what 19 cubed is. That's so when we cube both sides, that will kill the cube there. So that's oh lovely, 6,859 is equal to 9 plus C, from where C is equal to 6,850. See, now you have the value for C, and now you can write that y of x, right? Your function is cube root of 9x plus 6 ln of x plus 6,850, right under the square root. This is known as particular solution. And you can only have the particular solution if you have the initial point. If they never give you the initial point, you can't compute C, and then you have the general solution. So be very careful, right? In MyMATLAB, if you have the point, you go ahead and compute C, and then you plug that in. Now, if you don't have the point, you will have to use capital C in MyMATLAB. They will mark you wrong if you put the lowercase c in it. So just to add a little bit, right, to the annoyance of the software, which is awesome. So pay attention there, right? Always plug in capital value for C. A few more things that I wanted to mention here. When you are solving a couple of the other ones, for instance, you're talking about what was that? Uniqueness, existence and uniqueness, right? They talked about partial derivatives. And then exact equations in, I believe, 1.6 also had partial derivatives. Partial derivatives are learned in Calculus 3. I do have lectures on my YouTube channel, but YouTube is filled with lectures on partial derivatives. So you can go and learn partial derivatives in any of those lectures anywhere there. I'm just going to go through the basic idea, which is what we generally need to survive through this course. We are not going to use partial derivatives in any other chapter other than just the first chapter in those two lectures. So partial derivative is denoted as this squiggly d, right? So you'll have df, let's say dx, and that's going to be partial derivative in respect to x. So partial derivative in respect to x. So now what does that mean? Well, when you look at the Calculus 3, you look at the quadratic surfaces, you look at all of these things, you guys are going to have a function of x and y as an input. So some of the functions in Calc 3 are going to be z equals f of xy. So you have two variables as independent inputs, and then z, which is technically your y, z is your height, and x and y would be on the floor, right, giving the spatial two-dimensional position. This would be known as a third-dimensional, right? Now, obviously, you can't apply a 2D derivative on a third-dimensional function. So what I am doing here is I am going to now talk about the partial derivative, which would be in respect to either x direction or respect of y direction, which means you are looking for the slope at which the surface is rising up or down. This is literally walking up the hill or down the hill, but only in the x direction or the y direction. If you want more than that, you will have to look directional derivatives, where you can actually walk in any direction, not just north south and east west. But if you want to go southeast, then you can figure out what the vector for that is, and then you take out 3. But for us, right, we can have a function. Let's say our function of x and a y is given as 3x to the 6 y to the 4 plus cosine y. See, this is a standard function, right? It has a little bit of polynomial, a little bit of a trig, right? It's cool. And now what I can do is I can take partial derivatives in respect to x to see, to calculate, if I want to calculate the slopes, or in respect to y. So partial derivative of the function in respect to x, right? It's also denoted like this, but that's Calc 3, is going to be this. See, x becomes your variable and y becomes a constant in this case, because when you are walking right, left, and right on x-axis, the y on x-axis is constant, right? So we will be either copying y's or ignoring y's depending on the situation. So when you look at the first term, if x is a variable here, then 3y to the 4th is a constant. So we're going to have 3y to the 4th, that's a constant which we copy, and then I have 6x to the 5, which is the derivative of x. And then there are no x's here, so that's going to be plus big fat 0 right there, because the derivative of a constant is 0. Remember, y is a constant in the eyes of the differentiation with respect to x. So derivative of a constant is 0. So now all I need to do is to clean up this mess, and I'm going to have it as 18x to the 5, y to the 4. So this would be my partial derivative in respect to x. And then partial derivative in respect to y for the same function. Great. 3x to the 6 is my constant, copy it. And then derivative of y, because I'm taking derivative of y, is 4y cubed. Now, over here, y is a variable now, right? So I am going to have a derivative there. Derivative of constant is negative sign, so minus sine y. So this time around, this term survives. So this means now that when I fix this, it's 12x to the 6 y cubed minus sine y. Ta-da! There it is. So partial derivatives will be used again, right, in uniqueness, right, existence and uniqueness theorem, and it's also used in exact equations. And I would like to work out the problem you guys had the issue with. I received 3 emails, from different students, right? So 3 separate emails having trouble with the 1.6 problem, which had the whole partial derivatives and whole stuff like that. So let's take a look at that section 1.6, problem number 1, which was given as x plus 2y. And they did put the, like noobs, y prime equal 4x minus y, right? But since we are pros, we are going to put x plus 2y dy dx equals to 4x minus y, because we know that we have to ship dx to the other side. Now, first of all, this is not separable, right? Because you cannot separate x's and y's, right? Because you have pluses and minuses and all these kind of things, right? So that goes through the window. So the only thing we can hope for here is going to be exact equations. Now, exact equations have that form of m dy plus m dx n dy equal to 0, right? That will be the form. By the way, it would be really beneficial for you if you started a list of what the equation looks like, roughly, and then what is the appropriate method to solve that equation, because we are going to have a lot of different things coming up. So, the more categorization and more organization you do now, easier it would be for you guys to keep track of everything we cover. We'll cover a lot, which in actually grand scheme of things or math is very little, but the course has a lot, so keep track. So what am I going to do here? I'm going to ship this dx to the other side. So I'm going to have my x plus 2y dy equals to, and now these parentheses have to be put here because dx multiplies both terms. Now it's time to move dx to the left. We get negative 4x minus y dx plus x plus 2y dy equals to 0. Yeah, we're getting closer. I'm going to put this minus inside, and what it does is just swaps the terms. Right, that's the basic algebra there. And there we go. You have your mdx plus ndy equal to 0, and we know that we are supposed to check, right, the condition. I'll write that condition in blood. Condition for exactness is partial m in respect to y needs to be partial n in respect to x. So that's something that, again, you learn from the book, right? And then you apply it, right? It's in theorems. You learn theorems because those are the ways to solve problems. So what do I have? I need to take partial derivative in respect of y minus 4x. So what is the partial derivative there? Well, the derivative of y is 1, and the derivative of this one is 0, so it's 1. Now, partial derivative in respect to x of the other one, which is x plus 2y, is 1 plus 0, which is also 1. Well, 1 equals 1, so we're good to go, right? The equation is exact. You have to check this. It is not given that every problem will be exact. Otherwise, we would not have a book on differential equation, right? We would have a paper with 4 pages and that's it, right? And we'll call that differential equations. So you cannot use this method for every equation you see. Therefore, you have to check the condition. If this doesn't hold, the method cannot be used. Maybe you can use the method, you're going to get the garbage solution. But the thing is that, right, this has to be checked, right? It's not there for decoration. You have to check this first. and then you can go and do the problem. All right, cool. So the solution says that if the condition, right, for exactness is satisfied, right, you can go and you can integrate your m in respect to x, and do a little bit more work to figure out the rest of it, and you're done. So we're going to integrate m dx to get our part of the answer. Let's go it that way if you wanted like a step or something. So what is my m? It's y minus 4x dx, right? So that's what I am integrating. Now again, y is a constant. If I am differentiating or integrating in respect to x, then y is a constant. So integral of a constant y is just going to be yx. Okay, so that's yx. And then we have minus 4x squared over 2. And here is something new, plus c of y. Why c of y? Well, remember that I have two variables. I have a variable y and variable x. But I am integrating in respect to x, right? So integration is thinking that y is a constant. But we know that y is a variable. So this could be some function of y, call it y squared, let's say, and taking the derivative of it, right? Taking the derivative of it would still give you 0 and bring the solution back into this, right? So this could be a number, but it also could be, e to the y, sine of y, y squared, y to the 7th, right? It could be any function of y or a number, right? So that's kind of new from what you learned in Calc 1 when you just had plus c, right? Plus c means constant, a number, and you're done. But this could be also a function of y. So now what we learned is that this answer that we are looking for, which is f as a function of x and y, is actually given to us as xy minus 2x squared plus some c, which maybe is a number, maybe is a function of y. So this is a partial answer, right? You see how I said part of the answer? Because we are still wondering what is this, right? Most of the answer is already there, right? We have all of this mess. So all I need to do is to figure out how much is cy. Now, how am I going to do that? Well, I'm going to take the partial derivative of f in respect to y and equal that to n. And that will give me a new equation to solve. So, partial derivative of f in respect to y is equal to, remember, partial derivative of y, so x is a constant, so there is x. There are no y's here, so minus big fat 0, plus some derivative of c of y. That could be a function of y, right? If that c ends up being a number, well then that's a 0. But if it's y squared, let's say, then it's 2y, right? So we have to keep it as some kind of y. And remember, I'm equaling this to n. Now I have to go back to the beginning of the problem and find that my n is over here, x plus 2y. X plus 2y. I'll write that red. X plus 2y. This is n from above. So the left-hand side of this equation, which is x plus c prime of y, is from our derivative, and the right-hand side is from n above. So now, when these x drops, you get the equation, right? That, and now you can do this like a pro, right? This is derivative of c dy, right, is equal to 2y. That's this equation. And now separation of variables, dc equals 2y dy. Hit both sides with the integral sign, and you get that c, which is a function of y, remember, is equal to y squared, nice, plus some constant c. You can put k, you can put whatever, a, I don't care, right? So this c is not to be confused with this c. This is a c function, this is a c constant, right? So, so there we go. I know that c of y is y squared plus c. That goes in here. So, what's my f of xy? The solution. F of xy is equal to xy, what was it? Minus 2x squared plus y squared plus this big fat c. Now, what they want you in MATLAB, right? It's very important to read the form. They want you to put the answers in because you'll be redoing these problems 7,000 times. They did not code many answers. So, hitting the exact one they want is a challenge. So just, you can redo the problem and just remember the form of the answer. So you put your answer in that form, it should be good. So they want you to put xy minus 2x squared plus y squared equals c. And again, before you get triggered, right? Oh, it should be negative c. Again, negative c is negative 1 times c, and I just told you earlier that when you are multiplying or dividing c by a number, I don't care what it is, it gets absorbed in c. And when I type this answer, this is obviously a general solution, right? Because we don't have the value to calculate c. I got fantastic from my MATLAB, which made my day. So yay. The last pointer, even though I am going to put this in Canvas as announcement, is once your homework expires, you can still access the homework and much more through Study Plan. So when you are in My MATLAB, use Study Plan, click on all chapters, and then pick what you need. Pick any to practice. So that study plan is all of the problems that the software offers are in there. You can go, between any chapters and practice literally anything. It is open 24/7. There are no due dates. There is nothing, and you can keep practicing until you pass out. So that's it, troops. I will have finally office hours and everything set so we can all meet on Microsoft Teams. Please look for that email. I am going to post this video on in your modules and the announcement, so you will be able to get to this, and hopefully we can from now on communicate more directly, rather than just the email and Canvas announcements. Adios.